Hi, welcome to this video. Today we're going to be going through a walkthrough step-by-step of how you can get GPU accelerated static analysis in nTop. So to get started, if you haven't already, go to the link in the description. You can get to the Sileom homepage, and from there you can download a trial of Sileom Simulate that you can install and use to follow along with this video. So once you do that, install it, follow the directions, bring up nTop, and then we can get started. So the first thing we'll look at is connectors. Sileom Simulate is a connector plugin for nTop, so all of its features are exposed as blocks, which are defined through the connector here. So we define boundaries, model settings, a run block, displacement, constraints, and loads. So what we're going to do today in this example is a basic cantilevered beam. Now this is going to follow along mostly with the getting started guide that you'll also be able to find in the download package. So for a cantilevered beam, we'll define the beam with the box. We'll give it some dimensions. Okay. Take a look at it. So there's our beam. So I think what we'll do here is we'll fix one end and apply a downward traction load on the other. Now, the way we define surfaces with Sileom Simulate is through supplemental implicits. So these are just other implicit bodies whose intersection with our original implicit is going to define the surface that we want to work with. So first, let's go ahead and define those. Let's turn this into a variable because we'll be using it later. Okay, so we'll define a box to cover this end. We'll call this the base. And to get this to intersect with the original and cover the surface that we want, basically we're going to want the width and the height to be the same. We'll extend it across a little bit to make sure we cover the whole thing. And then we're going to have a small dimension in the length to minimize how much overhang we have. So we'll make the length something small, 200. The width, say 50. Height, say. Okay. And then we'll center this off in the end. Sometimes in order to help myself visualize these things, I'll make them transparent. Let's see. Okay. So we can see the base end covered there. Now let's add another one to cover, to define the other end of it. That's the end. Define sort of similar dimensions. We'll put it at the other end. Again, to help visualize, we'll just give it some transparency. All right. See it there. You can see both of our surfaces in isolation here. Okay, so now that we have the surfaces, we need to put them in a form suitable for Sileom Simulate. So to do that, first we'll bring in boundary, our first Sileom Simulate block. We'll discuss some of these options here. So this is our geometry. So we'll make this base boundary. We'll bring in our base. And let's see a few other options here. Now, like I said, the surface is going to be defined by the intersection of these two implicits. But that covers a little bit more than what we really want because we have overhang on the side. So the way we can refine it further is through the use of this constraint direction. So basically we define a direction through a vector, and then we define the surface that we want to only be that surface whose outward pointing normal is within some threshold of this defined direction. So by using this, we can exclude all of these overhang regions here, which typically we don't want. So we'll go ahead and do that. We'll set the constraint direction. This surface here points in the outward surfaces in the positive x, so we'll leave that as is, and we'll give it, say, 30 degrees. The overhang is orthogonal to this face here, so we could use pretty much anything there, but 30 is more than enough to cover it. Now we'll bring in a boundary for the other end. Bring in our implicit. Again, we constrain the direction. This one, the outward normal, is in the opposite direction. So we give it -1. And 30 degrees should be plenty. Okay. So now that we've defined the boundaries, we just have to associate the conditions with them. So the first one is a displacement restraint. This one's going to be fixed. So we have some options here. The boundary itself that we just defined. And then for this one, we need a working directory for Sileom Simulate to put some of its temporary variables in. And lastly is an ID. In order to handle numerous boundaries within a single notebook, they all need to have a unique identifier on them in order to facilitate Sileom Simulate's ability to distinguish them. So this is just a single identifier that has to be unique. It has there's no other conditions on it besides that. And we also need a working directory. So we'll grab a temporary directory block and put it in here. And to use this, we have to define we have to hand it some block onto which it should key off whether it needs to rebuild or not. So we'll just give it, say, one of our implicits for this. So we'll define these. We'll put in our boundary, base boundary, our working directory. And we'll start off with 0. Okay. And we'll give a load on the other end. This is our end boundary. We'll give it a small downward pull. Our units are all defined in millimeters, but Sileom Simulate works with meters, so this is in newtons per square meter. And then our working directory. And another unique ID. So we did 0, this will be 1. Okay. Into a variable. Okay, now we're ready to start defining parameters for our simulation. We'll bring in a model block. Model is the block that defines a lot of the parameters that are going to govern the behavior of the simulation. Let's go through these. Geometry, this is just our beam. Now we want the maximum element size. Sileom Simulate uses an immersed boundary method, which has a grid associated with it, where the size of the cells of that grid are used to resolve features in the geometry. So we really want to pick this to be something that can help resolve features that we have. The smallest feature in this case is really just the size of our bounding implicits. which, yes, the bounding implicits are also features that need to be resolved, so that also has to factor in to this size. In this case, we have a width of about 200 millimeters, so we can pick an element size is probably about half that, half of a characteristic feature size is usually a good choice for element size. So we'll go ahead and put that in here. Sileom Simulate takes everything in meters, so specify that 100 millimeters there. Compute levels. So that background grid that we use does undergo some adaptive refinement over the boundary. If we feel that the simulation isn't as accurate as it should be along the boundary, we can increase this to do some further refinements. A good starting point is just to use the grid as defined. Integration levels is also a refinement that's used to get a better estimate of surface features. The advantage of integration levels is that it does not incur as much a performance cost as refining the computation, as this only plays into, well, as the name suggests, the integration. So we'll go ahead and pick 2, which is often a good starting point as well. Shape order, linear, quadratic. Define some material properties here. We'll just stick some numbers in. Density, if we want to have gravity in the simulation. So now we've defined the model. Let's go ahead and bring in our run block that we'll use. Bring in the model we just defined. We'll bring in our boundary conditions, fixed boundary, and our load boundary. We need our working directory. Visualization levels is just defines how much resolution, how many refinements we want to take in order to visualize our results. A good value for this is usually the same thing as we use for integration levels. And then we have single precision or double. Consumer GPUs are very often significantly faster in single precision, so you may want to use that. But in our case, we'll just start with double. So now we've got everything running here, everything set up. Go ahead and run our simulation. Go ahead and turn off some of our visibility. Make things look better. Run it. See, we get a little progress bar and some information. Turn that off. And here we have our beam, displacement, stress. So, as you can see, very painless, and of course, very fast. So, with just a few steps, you can have GPU accelerated static analysis, no meshing. If you have any questions, please drop a line to support@sileom.com. Feel free to go to our website, and of course, feel free to comment and like the video. Thank you very much.